Okay, here's the problem we started on Friday, or we did on Friday actually. And if you look at this, it just says use a circuit on the right and complete the chart below. And the problem occurs, or the frightening thing occurs, is because we have more than one voltage source. We have a 24 volt voltage source and an 8 volt voltage source. And if we only had one voltage source, then we could find the REQ and reduce it down to a simple equation, a simple circuit that has one battery source and one equivalent resistor. But that's not the case here. So we have to utilize Kirchhoff's voltage law and Kirchhoff's current law. So when I first start that, I have to assume a current flow. I've identified node A and node B here. And then I've also identified current. I2 is the current going through the middle, and it's traveling from left to right. I1 is the current leaving node A, and it's traveling counterclockwise around loop 1. I3 is also leaving node A, and it's traveling clockwise around the bottom loop. So we have three currents, I1, I2, and I3, and we've designated which way they are traveling. Remember, if we get a negative answer for any of these, then we've assumed the wrong direction for current flow. Just like in civil engineering, we assume the wrong direction for tension or compression. So let's look at this. Let's do Kirchhoff's current law first to get our first equation. And if we look at node B right here, we see that I2 is equal to I1 plus I3. So let's just write I2 equals I1 plus I3. And that's going to be our equation number 1. I'm just going to highlight that, equation number 1. Okay, so next we're going to use Kirchhoff's voltage law to look at the looping, or look at the loops. The top loop, we'll call that loop 1, and the bottom loop, we'll call that loop 2. So if we look at loop 1, and we're going to write Kirchhoff's voltage law for that. I'm going to come in and change my paragraph. Okay, so if I look at that, I'm going to start at node B, and I'm going to, again, we assume current flow is this way around the loop. Current flow is counterclockwise. So if I start at node B, I'm going to get 8 ohms times I2 plus 8 volts. Then that gets node A, and it splits, goes up to I1, and it's plus 24 volts plus 4 ohms times I1. And that, now back to node B, and that equals 0. So I can solve for combine like terms and get current on one side and the voltage on the other. If I do that, I get 4I1 plus 8I2 just plus 8I2 equals negative 32. I can divide through by 4 just to make the numbers, smaller if you want to. So that gives me I1 plus 2I2 equals negative 8. And this becomes our equation number 2. We'll highlight that. Perfect. So we need one more equation, and that's going to come from loop 2, Kirchhoff's voltage law around loop 2. Okay, so let's look at loop 2 now. It's the bottom loop, and we'll go with loop 2. We're going to write the Kirchhoff's voltage law for loop 2. Okay, again, I'm going to start node B, and my current I2 is traveling to the right. Get to node A, it comes down, I3 comes this way, and so we have this kind of motion that we've assumed right now. So let's start at node B, and that gives me 8I2 plus 8 volts plus 8I3 is going to equal 0. Okay, and I can get my knowns on one side and unknowns on the other. That gives me 8I2 plus 8I3 equals negative 8. And now this gives me equation number 3. Now I have 3 equations and 3 unknowns. And thanks to Mr. Sandlin, we know how to solve our systems of equations. So let's see, if I look at loop 1, I have I1 plus 2I2 equals negative 8. But if you look at my equation 1, I have I2 defined in terms of I1 and I3, correct? So I can substitute in for I2. Let's go ahead and do that down here. So after I substitute in for I2, I'll get I1 plus 2 times the quantity of I1 plus I3 equals negative 8. And so I'm going to, let me reformat this. So now I'm going to just distribute and combine like terms. That gives me I1 plus 2 I1 plus 2 I3 equals negative 8, which yields me 3I1 plus 2I3 equals negative 8. Now, if I look at my loop 2 equation, and again I'm going to substitute in for I2. Again, I'm getting it from equation 1. I'm going to substitute in. And actually, I'm going to go ahead and divide through by 8. So before I substitute, let me change that equation. I'm going to get I2 plus I3 equals negative 1. So actually, this is our new equation 3. Sorry about that. Just like working with smaller numbers. So this is our new equation 3. That one is no more. Okay, so now let's substitute in for I2. And so if I do that, I get I1 plus I3 plus I3 equals negative 1. So then I get I1 equals negative 1 minus 2 I3. Great. Now I have two equations again. I have I1 in terms of I3, and then I have the relationship on this side between I1 and I3. And I'm going to call this equation 4. And let's see, that equation 4 and this equation 5. Okay. So now what I'm going to do is I'm just going to substitute what I know from equation 4 into equation 5. And once I do that, I'm going to substitute in. I'm going to substitute in for I1, and that's going to yield me 3 times negative 1 minus 2 I3 plus 2 I3 equals negative 8. So I do the math on this, and that gives me negative 3 minus 6 I3 plus 2 I3 equals negative 8. That gives me negative 4 I3 equals negative 5, or I3 equals 5/4 amps. Correct? And so the positive means that I've assumed the right direction, so we're good. So there's part of my answer right there. So I3 is 5/4 of an amp. I can substitute this now into equation 4 and get I1. And if I do that, I get that I1 is equal to negative 1 minus 2 times 5/4. That's what I said it was. And if I do that, I should get that I1 turns into negative 3.5 amps. So there's my I1. And that just leaves me I2 to solve for. And I can use my very first equation, equation 1, to solve for I2. So now I have I3 and I2, and I can substitute those into equation 1, or equation 2, or equation 3. It doesn't really matter, but I'm just going to use equation 1. So I have I2 equals 5/4, or excuse me, negative 3.5 plus 5/4. And so I2 should give me negative 2.25 amps. So now I have all three of my currents. I can substitute those back into my chart up here because the current going through the 4 ohm resistor is I1, and I1 is 3.5 amps. And so the voltage drop there is just V equals IR. So that will give you a voltage drop of 14 volts. I've already put volts up top. And then if I do the current going through the 8 ohm resistor right here, that's I2. And I2 is 2.25. Remember, we're going to lose a negative sign. We just assumed the wrong direction for current flow. I2 is actually not going from B to A. It's going from A to B. But we'll lose a negative there. And so then the current, the voltage drop across that is 18 volts. And then if we look at the last one, this one right here, the current going through that is I3. And that's 5/4 of an amp, or 1.25. And then the voltage drop across that is going to be 8 times 1.25, which gives us 10 volts. There you go. And then to get the power, we just say V times I. So it's 14 times 3.5, and that's 49 watts. The units are already up top. Again, it's just power is volts times amps. And it's 18 times 2.25, and that gives us 40.5 watts there. Again, it's just power is volts times amps. So that's 10 times 1.25, and that gives us 12.5 watts. Okay, great. Use this to help you solve today's work. Thanks.